You've probably seen this graph a million times, right? Economic equilibrium. But what if I told you that that simple little drawing from your Econ 101 class is missing the most important part? Yeah. To find it, we need to stop thinking like an economist and start thinking like a physicist.
All right, here it is. Yep, that's the one. Page 1 of pretty much every economics textbook ever, the famous supply and demand curve. Where those two lines cross, that's it. You get the equilibrium price. It's simple, it's clean, and it's definitely familiar.
But hang on a second. Have you ever really, truly stopped to ask why? I mean, what force actually makes the price stop changing right at that specific point? The graph shows us where it stops, but it doesn't tell us how. And that, right there, is the real mystery we're going to dig into today.
To get our answer, we've got to step outside of economics for a minute and wander into the world of physics. Because, as it turns out, that simple picture has a pretty fundamental flaw.
And this slide, this right here, it just lays the whole problem out perfectly. See, for an economist, equilibrium is where the quantities of supply and demand are equal. But for a physicist, equilibrium means something totally different. It's where the net forces acting on an object are zero. And those are two completely different ideas.
So here's the crucial point. We have to start thinking of the desire to trade as a real actual force. For a price to genuinely stop moving, the net desire to trade has to hit zero. The push from all the buyers has to perfectly, exactly cancel out the pull from all the sellers. The forces have to be balanced. And that brings us to this huge, missing piece of the puzzle that the classic model just completely ignores. What's the mechanism that actually balances these forces and brings the whole market to a grinding halt?
Well, the famous economist Alfred Marshall, he pictured it like a pendulum. He argued that if the price gets knocked away from that sweet spot, these restoring forces will always push it back to the center. And that sounds pretty logical, right?
But here's the major flaw in that analogy. Think about a pendulum in a vacuum, with absolutely no friction, no air resistance. It would just swing back and forth, forever. It would never actually stop. And the same thing goes for a market. Without some kind of friction, prices would just oscillate up and down endlessly, never truly settling.
That missing ingredient? It's friction. In economics, friction is things like competition, transaction costs, all the little things that slow stuff down. These are what we call dissipative forces. They literally remove energy from the system, which allows it to finally settle down. You could even say this economic friction is the true identity of Adam Smith's famous invisible hand.
Okay, so with that in mind, let's build a new model. Let's build one that actually includes this essential idea of friction and shows us how a market truly comes to rest.
So instead of two crossing lines, picture this with me. You've got two blocks, one is the demander, one is the supplier. And they're connected by a damper, like a shock absorber. And that damper is our market friction. This is a dynamic system, not just some static picture.
So here's how it works, and it's actually pretty straightforward. First, you get an imbalance. Let's say the demander block wants to move faster than the supplier block. That creates pressure. Second, the damper, our friction, resists that movement, and in doing so, it removes that energy from the system, usually as heat. And finally, the whole system just comes to a complete rest. It reaches a stable equilibrium.
Okay, now prepare for the big aha moment. This new dynamic model doesn't actually replace the old Econ 101 graph. In fact, that old graph is hiding inside this whole process. It's not that it was wrong, it was just incomplete.
If you take this mechanical system, the blocks, the damper, all of it, and you just flip it on its side, guess what you get? The supply and demand curve. That static picture we all know is just a single snapshot, a frozen moment in time, of this much richer, dynamic process of forces and friction hard at work.
All right, so this is a really cool way to reframe a classic concept for sure. But so what? Why does looking at economics through the lens of physics and friction actually matter? What does it really tell us?
To get it, we need to bring in a really key idea from welfare economics. It's called Pareto efficiency. And basically, a market is in a state of Pareto efficiency when it's just impossible to make anyone better off without making somebody else worse off. You've squeezed out all the possible win-wins.
And this is the mind-blowing connection. A market at Pareto efficiency is the economic version of a physical system at maximum entropy, its most stable, most disordered state. It's that point where all the surplus, just like energy, has been perfectly and evenly spread out. There's literally nowhere else for it to go.
So, you see, reaching equilibrium isn't just about supply meeting demand, it's a process that's actually driven by the second law of thermodynamics. You can think of it like this. It's like heat spreading out in a room until every corner is the exact same temperature. This is a fundamental law of the universe, and it's playing out in our economy every single day.
And this gives us this stunningly powerful new definition. The invisible hand isn't some kind of magic or some mysterious force we can't see. No, it's the very real, very tangible process of friction generating entropy. It's the force that makes sure all the gains from trade get spread out until the system finds its most stable, most disordered state, equilibrium.
And so that leaves us with one final and kind of profound thought. If the fundamental drive of any market is towards maximum entropy, a universal, inescapable law of physics, what does that actually imply about all our economic policies and all our attempts to steer and control where the market goes? Definitely something to think about.